Okay, for part A, this is the diagram basically I drew out. Your vectors, there's going to be enough g because it's on an incline. If there's enough g, there's also going to be enough n. There is friction on this, and so friction has to be against this block of motion, so it has to be left. So that's friction is going to be Fs. Part B. Equation for inertia calculus is just integral r squared dm, but you can't have a dm as your respect to, because mass in this case is going to be constant. So I draw above. The density is basically going to be equal to mass over area. But you want this to be the change in m over a, because your goal is you want to have you want to take this dm out, so we need to take the derivative of this, so that'll be equal to dm over dA. Or I guess if you want, yeah, you can say change m over change a. You need a change in respect to something in order to take a derivative. Area of a circle is pi r squared, and the derivative of that is 2 pi r in respect to dr. So we can plug everything we have back in here. So pi equals m over a equals to your dm. Oh shoot, instead of area, we can just plug in the function we have here. Pi r squared over dm over dA is 2 pi r dr. If we isolate that, if we move this over, it'll be 2 pi r dr over pi r squared, there's an m here, equal to dm. So we have dm, we can plug it back in this expression here. Oh shoot. Your bounds are going to be from r to 0, and it'll be r squared. If you plug the dm's in, 2 pi r dm over pi r squared. Your constants are going to be the 2, the r squared, and the m. So you can just move those to the top. So it'll be 2 m over r squared. Your pi's cancel out. R squared times r is just r cubed in respect to dr. If you take the integral of this r cubed, you'll get 2m over r squared times r4 over 4 and r squared. If you take the definite integral of that, your r would go into here, so it'll just be 2m times r4 over 4r cubed, and if you put the 0 into r4, this whole thing changes to 0, so it'll be 0. If we simplify this more, we could take out a factor of 2, so this would turn into 1/2. The r squared and the r4 you can simplify down, so the r squared would get canceled out, and this would turn into 2. So make this clear, I'm going to put this as equal sign, and then that will be equal to 1/2 mr squared. Part C, according to part A, okay, first of all, let me just set up torque. Torque is the force perpendicular to your radius is I, angular acceleration. Your Fs and your R in part A, according is perpendicular, they make a 90 degrees, so it's perpendicular, so we can use the Fs. R equals inertia is 1/2 mr squared. Angular acceleration you also can write as A over R. The r's cancel out. Fs is also, you can write it down as Fn mu. You can do 1/2 ma. Another way to write Fn is mg cosine theta mu s equals 1/2 ma. Your mass cancel out. If you move the 2 over to the other side, you get 2g cosine theta mu s. Okay. Part D. If you think about Part D, where it says the pivot got shifted, it got shifted at the surface. So the pivot's going to be shifted here. So if we do what was it? We're going to set torque again. You cannot use Fs since the pivot is already at the surface. So it's going to cancel out the Fs. So the only other thing perpendicular, your force perpendicular will be your Fg of x, because Fg of x and your r create a 90 degrees. You cannot use Fs because the pivot is already on the surface. It's already on Fs, so it's going to get canceled out, and Fs will turn into 0. So it'll be Fg of x times r equals your inertia. We use parallel axis theorem because the pivot got shifted. So your initial pivot, which is at the center here, would be 1/2 mr squared, but since it got shifted down, we had to add mr squared too. And we could do a of r. Fg of x in this case is just mg sine theta times r equals 1/2 times mr squared is just going to be 3/2 mr squared, and your a over r. What cancels out is going to be your r's, also your m's. So it'll be g sine theta equals 3/2 a. If you move this over, you multiply the 2 here and you divide the 3 down to the bottom to get a alone. So we 2/3 g sine theta equals a. Part E, draw free body diagram. So once a block, once a disk. The block is going to have a Fg, because on the inclines, of course, it's going to have an Fn. Tension will be pointing this way because that's the direction that the string is going. It's going towards the disk, so it has to be pointing right, and the tension is the string. And in this case, your force acting against the block is Fk, because what's allowing the block to move is the disk. When the disk moves, since the block is attached to the disk, the block isn't doing any effort to move, because the effort, how the block is moving is through the disk. So when the disk moves, since the block is already attached to it, it's going to move. So that means the block is already in motion, and since the block is already in motion, we labeled that force, friction force, down as Fk, since the ramp does have friction. With the disk, it's also going to have an Fn. It's also going to have a Fg. Tension, the string is, it's going to be pointing, the tension will be pointing towards the string. The string is left of the disk, so you can put tension here. We put Fs because the disk is the one that's starting in motion, not the block. So if it's starting in motion, it's going to be Fs. And it's going to be smaller than the tension, because if Fs is equal or even greater, that means that the block isn't moving because there's too much friction. So that means that this can't even move. Part F wants acceleration. So again, we can use torque equals I angular acceleration. Your perpendicular will be Fg of x minus tension, because your Fg of x in this case will be downslope. But your tension, if you visualize it, the tension or the string is pulling backwards compared to the box. So since it's pulling backwards, it's against the motion. It's against, because FG of X is going to be pointing right. Your tension is going to be pointing left since the string, since it's like pulling backwards. So tension will be against this FG of X, and these both are perpendicular to your R. It'll create 9 degrees, so it's perpendicular. So you can say that that's a true function there. Your inertia, it's relating to the previous problem. So relating to part D, we said the inertia using parallax theorem is just 3/2 mr squared, so we can use that. And your acceleration is just a over r. Your r's cancel out, so you're left with fg of x minus tension equals 3/2 ma. Now we need to find tension. So in order to do that, we can set up Newton's second law. Your forces would be T plus Fg of x minus Fk. Your tension and Fg of x, okay, according to part E, your tension is moving right. Your Fg of x is also moving right, but your Fk is moving left. It's going against it, so we have to subtract it. Equals your Fn. We want to isolate. We want to solve for tension, so we have to isolate. So if we move it over, be tension equals Fk minus Fg of x plus Fa. Tension Fk is Fn mu k minus your Fgx is just mg sine theta plus ma. Your tension Fn is just mg cosine theta mu k minus mg sine theta plus ma. We have tension, so we can plug it back in here. So if we plug back in here, actually we can even simplify this Fg of x. We said Fg of x is just mg sine theta, so we could put mg sine theta minus your whole tension, so minus your mu k, mg cosine theta mu k. Since you're multiplying this by a negative, you're distributing the negative to all of this. So negative times a negative is equal to positive, so it'll be plus mg sine theta, and then plus mg plus ma is in here. You're distributing a negative. You're distributing a negative, so it'll be minus ma equal 3/2 ma. Your mass, all your masses cancel out. There's a g sine theta here, a g sine theta here, so we can just add both those up to equal 2g sine theta minus g cosine theta mu k equal to, and you can add this acceleration to the other side. So 3/2 a plus a equals 5/2. So it'll be 5 over 2a. If you move this over to get a by itself, you need to multiply 2 over to the other side. So if you multiply 2 to this whole function, not just 2g sine theta, the whole function, 2 times 2 is just 4, so 4g sine theta minus, if you multiply the 2, here, g cosine theta mu k, it'll be 2g cosine mu k. You need to move the, once you multiply the 2, we also have to divide the 5 too in order to get acceleration. So over 5 equals a. And we can also factor out a g. And that matches the expression that we want part F, so we're good. Okay. And here part G, force, show that friction force is acting on. You know what? Let me go back to Let me go to the first page so I have the diagram. G. So we set up torque again. We want Fs according to the disk diagram we already have. Fs and R are perpendicular to each other according to the disk. So we can, so since Fs and R make it 90 degrees, so it's perpendicular. So we can say Fs times R equals the inertia of a disk is 1/2 mr squared. And A over R is the angular acceleration. Your R's cancel out. Fs in this case is mu s. F of n, your F of n is mg cosine theta equal to 1/2 ma. Oh shoot, sorry, we're solving for Fs, sorry, my bad. We keep Fs here, my bad. Fs equals 1/2 ma. We already saw A is this function here, so we can just plug it in. D. So we can distribute this 1/2 to the numerator. So we get Fs equals mg 1/2 times 4 is just 2. So we can put 2 sine theta. 1/2 times 2 is just 1. So k cosine theta over 5. And that's part G that matches our expression. So move on. For part H, it's having a new scenario where the mass is just due to what happened in magnitude of the tension. Our tension that we calculated in part F is T equals mg cosine theta mu k minus mg sine theta plus ma. This is old scenario. Our new scenario is when the mass is turned into 3. So tension equals 3 mg cosine theta mu k minus mg sine theta plus, oh shoot, this is 3 plus 3 ma. If you compare the two functions, it's not really directly proportional because your acceleration for the new one, I should label this as A1 and A2 because your accelerations are going to be different because you have a bigger mass, so accelerations of course going to be different. There's a 3 mg cosine theta, there's just mg cosine theta. If you just compare both of them mathematically, this side is bigger because we're adding more numbers, so it's not really directly proportional, but mathematically speaking, a bigger mass will not really proportionally but lead to an increase in tension because this side is now bigger than this old side since we added more numbers into this new side. So we could say according to the function, even if T and M aren't really proportional, but in the function, if T, if M goes up, T in the most sense will also go up, which shows an increase in T. Okay, so I'm just saying that T is just going to increase because the side's going to be bigger when you have a 3M. Okay, that's it. Bye.